Hi Algebra 2 students. Today we start chapter 6, where you can see from this slide we will be talking about exponential functions, but as the chapter goes on we will also be talking about log functions. Today you can see that in section 6.1 we are going to be able to recognize the key features of these exponential functions. Day 1 we are going to identify the key features, so we're going to talk about domain, range, intercepts, asymptotes, and end behavior, and we're going to be able to graph them. Now, here's a situation where we're going to make some connections to things we've done in the past. Okay, so using this table, we can see that they've already filled in the y equals 3x table. So this is a linear function, right? 3 times x, that's linear. So they went through and they found the difference of the y's and also the ratio between the y values. Now, we've done the difference of the y's before. We haven't really talked about the ratio, but we're going to talk about why we need to look at that today. Okay, so we could go through and do the same thing where we could evaluate y equals x cubed. Well, if I plug in 1 for x, x or 1 cubed would be 1, 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. If I go to find the difference here, I would do 8 minus 1, which is 7, 27 minus 8, which is 19, and when I subtract 64 minus 24, I get 37. Okay, so you get the idea. So that we've done before, but we can see that these are not a constant difference like it was in the linear function. Now, if I find the ratio between the y values, so in this case, I would take 8 divided by 1, I get 8. I take 27 divided by 8, and I get 3.375. And when I did 64 divided by 27, I got 2.37 or so. So when we look at both those relationships, nothing similar. Okay, but now we're going to look at what we're going to do today. This is called an exponential, where we have 3 to the x power. Okay, so that's the difference. The x is the exponent this time. So if I take 3 to the first power, I get 3. 3 squared is 9. 3 cubed is 27. And 3 to the fourth is 81. Now, if we do what we did in linear functions and do the 9 minus 3, we get 6. 27 minus 9, I got 18. And when I subtracted 81 minus 27, I get 54. So we can see that that difference is not the same like it is in linear functions. But now let's look at this new thing, the ratio between y values. If I do 9 divided by 3, I get 3. If I take 27 divided by 9, I also get 3. And if I do 81 divided by 27, I also get 3. So what we can see is that the ratio between the y values is actually constant. Okay? And that's going to be what happens in these things that we call exponential functions. At the bottom, it just asks the question, which of the functions will have y values that increase the fastest as x increases? Now remember, for all three of these situations, we put in the same x value, 1, 2, 3, 4. The linear one stopped at 12. The x cubed graph stopped at x to the fourth, but what we can see is 3 to the x actually went all the way up to 81. Okay, so because we are taking it to a higher and higher power, meaning we're multiplying a big number by itself over and over again, that is the one that is going to grow the fastest. So 3 to the x is the one that grows the fastest. All right, so now that we've just done this investigation, we're really going to focus today on this exponential graph. So this is something that you definitely want to get in your notes. It says, what is an exponential function? It's any function of the form y equals a times b to the x, where a and b are constants. Okay, also we have to note that a can't equal 0. Now the next bullet point says a is the y-intercept. Now hopefully that makes sense, because the y-intercept is when x equals 0. Well, if I put 0 in for x, if I have y equals a times b to the 0, hopefully you remember anything to the 0 power is 1. So that's why the y-intercept is just a. Okay, so the a is the y-intercept, or you could write it as the ordered pair 0, comma a. All right, so b will never be 1. That's a key. And b is always going to be positive. Now, the one thing that this slide doesn't look at, and I'm just going to kind of give you an intro because it will come up through graphing things today, but there's another thing that's very special about b. Okay, so it's never going to be negative and it's never going to be 1. But it could be something between 0 and 1. And if b is between 0 and 1, then it's going to be decay, which means it's actually, when you graph it, it's going to go down from left to right. It'll look something like this. And if b is greater than 1, that's when you're going to have a growth situation. and that's when it's going to be going up from left to right. And we haven't even looked at the graph. We see one right here. This is an example of what it looks like. So this one would be an example of growth, okay, because it's increasing from left to right. Okay, so B would be greater than 1 for this example. Now, also in this example, the y-intercept is at 1. So I could also say that 1. Okay, so based on just these couple of things, we can identify that based on that graph, it's got a y-intercept of 1, so A would be 1, and B has to be something bigger than 1. Okay, so that is the basic foundation of an exponential function. But now we have to be able to identify the key features. All right, so what are some key features of the function f of x equals 2 to the x, including domain, range, intercepts, asymptotes, and end behavior? And we want to graph these to be able to really see it. And anytime we want to graph something that we haven't seen, we're just going to make a table of values. When we make our table of values, we always want to include negatives, we want to include 0, and we want to include positives. Okay, so all I did is, so this is f of x, so I'm plugging these values into 2 to the x. So 2 to the negative 2, when I did that on my calculator, I got 0.25. 2 to the negative 1, I got 0.5. 2 to the 0, we already talked about, anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. Okay, so even when I plugged in negative values, I got positive answers. So let's draw a picture of this. So at negative 2, I had a point at 0.25. It's super duper close to that x-axis, but it's not on it. At negative 1, it's here, and at 0, it's 1. Now, let's pause there real quick. This is the y-intercept. So connecting it back to what we just talked about, remember, this is f of x. It was just 2 to the x. We said it's going to be a times b to the x. Well, if there's no number in front, that's the same as doing 1 times 2 to the x. So my a is 1, which is my y-intercept. And now we saw it on the table as well. So there's that connection. All right, over 1, up 2, and over 2, up 4. Okay, if I trace these, I could keep going back. If I plugged in negative 3, it would get closer here, negative 4. But the reality is no matter what values I plug in, no matter how far to the negative side I go, I would actually never get 0. And that's going to be a really key fact in just a second. Okay, so this is what the graph looks like. Now, again, based on what we talked about on the last slide, my b in this case is 2. 2 is greater than 1, so that's why it's going up. It's growth from left to right. Okay, so now let's talk about the domain. Domain is the x value. So if I look at this, how far this graph goes to the left, okay, it has an arrow, so it keeps going to the left forever. It covers everything in between, and then it has an arrow that's going slightly out to the right forever, which means my domain is all real numbers. So negative infinity to infinity in interval notation, or again, you could be looking for all real numbers. Here's the reality, you guys. Just like parabolas when we did those last semester, all exponential graphs will have a domain of negative infinity to infinity because we're not going to chop them off unless it's a real world scenario. The range, however, this is different. Okay, range is the y values. So when I look for y values, I start by looking at the bottom of the graph and I work my way up. Because remember, with interval notation, we always want to start with the smaller value. And what I just highlighted the lower half of this graph, and that red curve doesn't go down there at all, which means it does not touch any of the y value or the negative y values. Okay, now this is where you have to be really careful. The next value I test, so I look at negatives, it's not down there. Then I look at when y is 0, which is this line right here. And I already said, no matter what negative x values I plug in, I could plug in negative 3, negative 4, negative 25, you're actually never going to get 0. We can see it's getting closer and closer, but it's not going to touch it, which means that the beginning value of our range is 0, but because it's never going to touch it, we can't include it, which means it's going to have a parenthesis. Okay, so that's one twist on the exponential graph, and we'll talk about what that is in a second. And finally, it does go up forever, so it's from 0 to infinity. Okay, if you were doing inequality notation, it would be y greater than 0, so you would not underline it. The y-intercept, we already talked about, that's the 0.01. Now, asymptote. Remember, asymptotes are lines that the graph approaches but never touches. Okay, so we've been talking about this very special x-axis in this case. We said it's going to get closer and closer and closer to it, but it's never going to touch it. That is called an asymptote. It's the line that it gets close to but never touches on the ends. Okay, now because this is a horizontal line, it's a horizontal asymptote, and horizontal lines have equations y equals, and since it's on the x-axis, it's y equals 0. Okay, so it is the x-axis, but it will shift, and so we want to be able to write it as an equation of a line. So a horizontal asymptote will always be y equals some number. So y equals 0, because that's the number it's approaching. Now, in behavior, that's where we're talking about what's happening on the two ends of the graph. So you will start with as x approaches. So you're saying what x is approaching. You could start with the positive infinity or negative. So let's go to the right first. As x goes to positive infinity, f of x, or the graph, approaches what? Okay, so we did this earlier this year as well, but as x goes to the right, okay, so we're saying as the graph goes further and further to the right, so we're talking about this end of the graph, the right side. So this is as it goes right. In words, graph goes what? And in words, I would say up. Okay, so your answer is it going up or down? And if it goes up forever, that's when it goes to infinity. Okay, so your answers for end behavior could be positive infinity. If it was going down forever, it would be negative infinity. And now we're going to see one twist. As x approaches negative infinity, f of x approaches what? Well, again, this is as it goes left. The graph goes, when it goes left forever, this arrow, it doesn't keep going up forever. It doesn't keep going down forever. It goes right along that x-axis. Remember, we said it never touches it, but it gets closer and closer and closer. It actually goes to 0. Okay, so when you have this horizontal asymptote, one of your end behaviors will be the value of the horizontal asymptote because the graph is going to approach it on its end. Okay, so that's how we identify key features. I'm going to pause the video. Or you're going to pause the video, I should say, and I want you to find the key features of this graph. Unpause and see how you did. Okay, so you might have wanted to make a table. If you did, you would have continued to use these values. But before you did that, maybe you just looked at it and you said, oh, there's a 5 in front. That's going to be the y-intercept because that's the a value. So you could have said my y-intercept is 0, 5. Maybe you even got to the point where you recognized B because I told you that on the front end, even though this was supposed to be kind of exploration. B is less than 1, which means it's going to be decay. So the difference is it's going to be going down from left to right, which is going to change slightly. Okay, so you could have looked at that, but let's really look at the graph. So when I plugged in -2, I got 20 this time. -1, I got 10, 0, 5, 1, 2.5, and 2, 1.25. So when I went to graph it, -2, we'll say 20 is way up here, -1, 10, 0, 5, 1, 2.5, and 2, 1.25. Okay, so when you graphed it, you should have seen this. You might have had to go a little further to see that you, again, no matter how big the numbers get, if I put in 5, I would still get something that would never be negative, and it would never touch 0. So we basically flipped the graph. It's now going down from left to right, but actually most of our things stay the same. Your domain was still negative infinity to infinity. It still covers everything. The range, it still never goes down below the x-axis, so it's 0 to infinity because it also will never touch 0. So make sure you put that parenthesis instead of a bracket. The asymptote is y equals 0 because that's this horizontal line that it's getting close to but never touching. The only thing that changes when we switch to decay is end behavior. This time, as x approaches infinity, f of x approaches. Now we're saying as the graph goes to the right. Well, on the right side, that's the side that's actually approaching that asymptote. So that one was 0. And then as x approaches negative infinity, f of x approaches. As I go to the left forever, I've got this arrow, which is going up forever, so that's positive infinity. Okay, so it just switched those things. All right, now The next thing we have to be able to do is we have to be able to graph transformations. The good news, you guys, is our rules of graphing transformations has not changed. I'm going to write this off to the side. So the rules of transformations. Again, it hasn't changed. All that's changed. So we now have f of x equals a times b. Now we are going to have something in the exponent with the x and then the plus k on the end. So we still have that x minus h plus k. The difference is how it's grouped with the x. This time it is considered grouped with the x if it is in the exponent with the x. Okay, we've done this with quadratics, we've done it with square root graphs, we've done it with cube root graphs. Okay, but we've said that as soon as it's grouped with the x, so this time in the exponent with the x. That's the only thing that changes. That's when it goes left or right, and it's the opposite, what you think. Okay, the plus k on the end. So if you're adding or subtracting a number that's not grouped with the x, so not in the exponent, that is going to move it up or down the same as what you would think. Okay, so this plus k will shift it up or down exactly what you think. Those rules haven't changed. Okay, don't forget also a negative a, because that's outside of the x value, right? So a negative out front, that is multiplication, which is going to be a reflection. And because it's not with the x, it reflects it vertically. So that would be a reflection over the x-axis. Now, one note, just so you know as you move forward, we don't do much with it this year, but you always have to reflect first. If you're doing multiple transformations, you must reflect first if you're going to graph it. Okay, so in this one, we're going to look at these transformations. So when I look at g of x equals negative 3x, really the only thing that changes is what we just said. That negative is going to be a reflection over the x-axis. Again, from the parent function. So we're looking at 3 to the x, which means its original before the negative would have had a y-intercept at 1, and it looks like this. So if I take that graph and reflect the whole thing down over the x-axis, that means that this key point moves to 0, negative 1, and all these points flip upside down. Okay, so this is the graph. It's g of x equals negative 3x. 3 to the x, sorry. Okay, it does ask me what happens to my asymptote. Well, my asymptote actually didn't move. I actually reflected it over that. It's y equals 0 is the asymptote. Now my y-intercept with that reflection did change. It was at 0, 1, now it's at 0, negative 1. Okay, so it might ask you to do some transformations and ask what happens. Okay, I want you to pause the video and ask yourself what happens in B and then unpause. Hopefully you're able to identify that the negative 4 is after everything, so that is actually going to move it down 4. Which again means I take what was originally, so 3 to the x would have looked like this. Now this is where you would actually take the asymptote that was at 0, and that asymptote moves down to negative 4. Okay, so we will move our asymptote with a vertical shift. The point that was at 1 moves down 4, 1, 2, 3, 4. The y-intercept moves down to 0, negative 3. Okay, everything else stays the same. So a shift up or down does in fact move the asymptote and the y-intercept. All right, last but not least, one last example. Again, you can pause it and try it. You might not be able to talk about the y-intercept. We'll talk about that in a second, but go ahead and graph this. Describe what happens to the transformation and what the asymptote is. Okay, hopefully you were able to identify that the x plus 3 was on the exponent, so it's left or right the opposite of what you would think, so it's actually left 3. This one's 5 to the x, but that's the same as 1 times 5 to the x. So the original graph before the shift would be here. This is just 5 to the x. So if I move that left 3, 1, 2, 3, I take that y-intercept, it's now over here. So the critical point is now at negative 3, 1, okay? But it doesn't affect the asymptote. So my asymptote is still y equals 0. When I shift it left and right, it doesn't affect the asymptote. But the other thing it does change is the y-intercept. it moves it. It's now up here, so I can see it's higher, but I don't know exactly what that is. If you're asked to find the y-intercept in one of these that shifts left or right, remember the y-intercept is when x equals 0. So you're actually just going to have to calculate that algebraically. So I'm going to do g of 0, which is 5 to the 0 plus 3, which is 5 to the third, which is 125. Okay, so clearly my graph is not a good sketch now that I look at it, because the point is at 0, 125. I did not show how fast this is increasing. Okay, so this would actually look something like this, and it would cross way up here. It's still not far enough, okay, but it would cross way up at 125. Now, I know we didn't bring it up here, but in all reality, I'm hoping the first thing that pops into your mind when we're talking about exponential growth is the coronavirus, right? From the beginning, you've been seeing graphs on the news that are showing this exponential growth curve. So this is a real world application. We'll get into that later as time goes on. But this is the situation we're talking about when we talk about COVID-19. All right, go ahead and work on your 6-1A Pearson practice. Thanks.